Welcome, everybody. Good morning. Welcome to OPAL-RT Learning Journey. Today, we'll be talking about the eVTOL HIL testing to accelerate the future of air mobility. So myself, Alexandre Leboeuf, I'm the Aerospace Business Unit Manager at OPAL-RT. Rapidly, my background is electrical engineering. I've been working with OPAL-RT for the last 15 years or about. And of that timeline, in the 15 years, perhaps 13 was in systems integration, and the last 2 years and a half I was aerospace business unit manager. So I decided to focus myself on the aerospace market. I'll be presenting today with Yon Bonaru. If you want to present yourself.
Yep, thank you, Alex. I'm Yuan, and I'm aerospace system integration specialist, and I work mostly on custom solutions for clients for the past year at OPAL-RT. And for the demo that we'll be seeing today, I worked with two other colleagues from OPAL-RT, and I hope you'll have as much fun enjoying it as much as I did working on it. Thank you, Alex. Back to you.
Thank you, Johan. So here's the webinar outline. So our quick introduction, which is already done. After that, we're going to go to my section, which will be HIL, an overview, where we're going to be discussing a little bit how the HIL will be helping on the aerospace and more specifically on the eVTOL front. After that, we're going to go to the demo, the eVTOL HIL testing demo presented by Johan. And after that, there will be a question period. For the question period, we invite you right away to include all your questions in the Q&A tab in the Zoom menu. We won't take any question during the presentation, but we will take question in that question period. So whenever you have your question ready, feel free to input it anytime, and we're going to go back to them after at the end. So that way it's going to prevent you from forgetting your questions, or sometimes you're going to be on the spur of the moment, have a great question, and we don't want to miss out on those at all. So without further ado, so HIL, a quick review. So basically what we can see is really that I think everybody knows what HIL is, right? Whenever I ask the question, what is hardware in the loop, I have a plethora of answers, which are all good, but I really like to take a moment here to actually highlight the differences between basic signal acquisition and actual hardware in the loop. Why is that important is why I'm showing this to you guys today. So the signal acquisition is not part of a functioning system with the DUT, the device under test, like an oscilloscope. So a lot of systems out there do just that, signal acquisition, which is, well, not which is, but really has a purpose in itself, because you want to debug, you want to monitor, you want to be able to just send some type of signal and to be able to do some small acquisition. That's a purpose in itself, and it's important. But the hardware in the loop is an integral part of the functioning system of the DUT, where we're going to have real-time computer systems, for example, interconnected with the device under test or the different LRUs that we will find in the aero market. The idea here is really to have the controller or the component think that it's actually inside the aircraft and the system that it should be working with, unlike the signal acquisition, which is mainly monitoring of what's happening. A factoid that is super critical to mention, because I've seen people asking the real-time computer to be as good as an oscilloscope to get 2 gigasample seconds. An HIL does not need to function at those speeds. We need to go, though, to, at the very least, respect the Nyquist-Shannon sampling theorem to be able to effectively convert the analog signals to the digital computer format. So that in mind, when you have your own system and you're wondering at what speed the real-time computer would need to be performing, I invite you to go back to the Nyquist theorem, and it's usually going at least twice the frequency that you need to acquisition. Obviously, to limit aliasing and other issues that have been discussed during the other webinars of the Learning Journey program. It's important to take into account that you might need to go further and higher in the frequency to make sure that you limit those type of issues. Okay. This being said, so why is a hardware in the loop system important? It's because of the certification effort in the eVTOL and aero market. Usually, a lot of the companies right now in the eVTOL segment have a flying prototype. But now what's happening after that? We all know that once you have a prototype, it's not said and done and you can sell it to anybody that wants to purchase your airplane. No, you need to go to the certification effort to be able to go to the production, and after that to the sale of your aircraft. Some of the challenges in the certification effort, and here I really want to highlight it's some of the challenges, not all by any means. I'm not pretending to be a certification expert here, okay, guys? So you probably know better than me. But some of the challenges that I've seen a lot is there's a lot of validation per the standards and the regulation. There are a lot, and in the eVTOL segment, there are undefined in some cases. So some standards may pop up during the next few years, depending on how and when things happen. So this will be a very tough challenge. You'll be needing to be able to adjust very fast. A lot of proof to document. So a lot of the results will need to be documented, reported to be able to find easily. Consistent results. So the same test should technically end in the same results. It's not always as easy as it sounds to get. A lot of subsystems, LRU, interacting together. So in the overall aircraft, there's a lot of subsystems that will be interacting that you need to validate. Which one will be faulty or producing the error is to be investigated, and it's a tough part. Test teams are usually not the one that design the systems. So they're not always super in the know about that specific design that has been used. And in some cases, the design does not necessarily follow what has been mentioned at the early stages of the spec. So this also needs to be adjusted as the validation goes on. And finally, the correlation between the simulation and real data needs to be done. Why is that? Is because the certification bodies will need to have proof that the simulation data that you've gathered with the hardware in the loop system will be representative of the real system. So you still need to have your prototype flying and the data acquisitioned with your real prototype flying, but all the tests won't be needed to be done on your prototype by itself if you can prove with the correlation that the data that you're obtained with the simulator is the same with the one that you've got with the airplane. So that way it limits a lot of the work that needs to be done. So what can HIL offer to help? So there's multiple type of test benches available. I'm pretty sure you already know some of those, mainly the Ironbirds. Why? Because Ironbirds were principally a lab replica of the whole airplane. So the size was usually the same to get the same number of feet in the cables, the same be said with the hydraulic system and so on. But nowadays with the Ironbirds, with the HIL system is coming more and more with an interaction of a lot of HIL systems that will be working together. Those systems are mainly system test station. Those test stations are usually set up per different subsystems, so one per LRU, like for example, for the landing gear, air management system, main propulsion engine, and so on. Closed loop benches will be more of the type at the R&D level. So your R&D teams may use closed loop benches that will go more in depth to challenge the actual controller. Then the system test station will be a bit more functional. EMI test benches, because well, we don't always subject our prototypes, flying prototypes to electromagnetic interference while flying. So we need to actually encompass that into test chambers, etc. All of that is really to create a safe environment to be able to do the test. Because in some cases, some of the tests, if the controller does not work well, might destroy your prototype. So imagine your brand new prototype for the main propulsion engine, and you need to do a test and the test fails and it actually destroys your motor. What do you do then? You just scrap a 20 million or so model. That's not going to cut it. That's where the HIL is coming into the rescue, basically, to be able to see if at least those test cases that might damage either the life of the pilot on the prototype or the equipment are validated prior to test flights or to specific tests. Also, it adds up to the automation and scripting. So basically, it gives you the capability of doing tests 24/7, which with your flying prototype is not necessarily easy to do. Understand that you can have a lot of test flight pilots, but at one point you need to recharge the batteries. There's a lot of challenges. So scripting is the way to go to be able to expedite and replicate a lot of the data. Data logging with timestamp is an easy setup also to be performing with the system. Specific validation of special cases. So you've seen something on the flight test, you need to reproduce it. You won't necessarily use your flight prototype again. You can replicate it in the HIL system. Cheaper than hours of flight. Obviously, running a PC in a lab is way cheaper than having to book the prototype for flying. And it's easy to do regression tests. So whenever you change something in the bench on the controller, it's easy to replicate all the validation and see if the results are still the same. Aircraft components maintenance. So a lot of the challenges that we face lately is the maintenance part. So after flying for a few hours, a few dozen hours, a lot of components need to be recertified to make sure that they perform as per spec. HIL can be translated once they've done their duty as the certification body test horse, can be reused, repurposed after that to be able to do some of the validation of some of the LRUs for recertification. It's not necessary to have an HIL to do that. Usually, a lot of the LRUs are simple enough that a simple acquisition system would do the trick. But in some cases, like for example, the main propulsion engine flight controller, well, you need to make sure that it's still perfectly fine. So you might need an HIL in those conditions. Now the battery challenge. eVTOL, with hence the E, is purely electric. So today's great challenges are coming from the batteries. The weight to power ratio is very low compared to kerosene. It's the same issue with cars, but it's way more critical for aircraft. The time to recharge is also important. On a car, you plug it, you go to sleep, but for an airframer and a company that does run your aircraft, well, that downtime is costing them money. So each time that the plane is out of commission for hours, it's time that is not making money and being profitable. So it's critical to limit the downtime. And finally, the dwindling capacity as the battery gets older. So there's a fixed number of recharge capability to be able to sustain sustained flight. So this also diminishes the capacity of using a battery for a certain period of time. Unlike cars, if it's little less, it does not impact. But for airplane, it might require the aircraft to be changed to another flight instead of a flight that would normally go 6 hours or 2 hours. Now it's limited to a 1 hour flight. It's kind of difficult. So it's one of the biggest challenges that we see. So we have limited short-term option as we speak. Optimize the propellers to be able to be more efficient. Optimize the other components' weight. So obviously, if we can replace the weight of the battery in other components, we're going to be winning. But one of the proposals that OPAL-RT and the other companies that do HIL is proposing is to optimize the inverter motor control. OPAL-RT has two solver approach, Artemis SSN, which is CPU based, and EHS, which is FPGA based. Basically is really to replicate the DC bus that you have, the AC side with the inverter, and finally the motor application that you have. So that's that for my part. Johan?
Yeah, thank you. So we recorded a video for convenience where we demo project where I don't want to go too deep into the technicals because it will all be covered in the video, but if I can give a little more context. So the beta aircraft has two pairs of motors for takeoff, which are redundant, and then there's a third one for propulsion. So we simulated the controls and one motor each independent for the takeoff and then for the propulsion. And all those we show how we did this demonstration on OPAL systems. I think we're ready for the video. When you're ready.
Hi, my name is Ian. I'm an integration specialist in the Aero business unit, and today I'm excited to show you a project where we will be simulating the powertrain for an electrical vertical takeoff and landing vehicle, or eVTOL for short, as illustrated here. I will first introduce the hardware and the software used, then I'll give a quick overview of the simulation architecture, and finally we'll demonstrate how the whole system works together, where I will be controlling an X-Plane 12 simulation using a joystick. First, we have the OP5707XG target, which is based on the Xilinx Vertex 7 FPGA. It has an analog output and a digital input module. Next, we have the OP8666 RCP controller, which is based on the TI C2000 microchip. Also not shown here, we have a PC running X-Plane 12 and a PC running the simulation. RTLab runs the real-time simulation. eFPGA Sim runs the inverter simulation on the FPGA using the EHS Gen 4 solver. We have RT Events that generates the PWM signals required to run the inverter switches. And finally, we have Code Composer Studio to run the model on the OP8666. Let's now take a closer look at the system being simulated. First, the powertrain is fully electric. In this case, we represent it by a solar panel charging a battery. Then we have an inverter, which converts the DC voltage from the battery into three-phase AC signals. We also have the motors, obviously, and the microcontroller, which is an outside system. This picture gives a better overview of the hardware-in-the-loop system. On the right, we have the target, which runs the motor and the inverter models. From there, we will extract some data. Those are phase voltages and phase currents and motor position. And we will feed this data into a physical controller, in this case, the OP8666. And it will take this feedback and calculate the appropriate PWM frequencies to generate in order to drive the inverter switches, which are simulated inside the target. The model itself is divided into 4 subsystems. 3 are for real-time simulation, and one is for data visualization. So first, let's take a look at the GUI. It allows us to monitor data from the simulation itself, in this case, the motor speeds, and also interact with the simulation. Next, we have the master. It controls the IOs to communicate with the external controller. It also contains the model for the 3 motors, and it interfaces with the FPGA using the EHS solver. Next, we have the FOC control module. It simulates the 3rd motor, and it also generates the PWM signals required to run the 3rd motor. So what's interesting to notice is that part of the model runs on the CPU, and part of the model runs on FPGA. So the part that runs on the FPGA is much, much quicker, and it allows us to have a much more reliable and a faster simulation. The part that runs on the CPU is still good enough, but it's not as powerful. The EHS block takes in DC link to power on the inverters. It also takes in some gate signals. This is used to control the inverter switches, and a scenario ID, which allows us to simulate faults. We'll get to that in a second. What is also interesting is that we have some outputs. Those, again, as we mentioned earlier, are some phase voltages, phase currents, and motor position. Here, we can take a look at the live demo of what this would look like. I have the simulation running. And now we're going to take a look at the first motor. As you can see, we're monitoring the phase currents, the phase voltages, and the motor position. We can see that the first motor oscillates around 472 RPMs. Same thing for the second motor. The same idea. Another advantage of using the EHS block is the ability to easily simulate faults. So the way it works is it allows you to modify any parameter for any passive component in the circuit, and then it stores that version of the circuit in the FPGA, and it allows you to swap between them during runtime. Very important. In our case, we simulate 2 types of faults with an inverter. One is where the switch is stuck open, or one of the switches or more are stuck closed. Having seen all this, we're now ready to take a look at the demo. We're now ready to take this eVTOL for a spin. It's a Elia 250 from Beta Technologies, which is integrated into Explain 12. We also have an RT Lab plugin, which communicates between the target and Explain 12. So let's take off. I'm not a certified pilot, so please hold on. We'll start by giving a little thrust to the 4 motors. So this should make the aircraft take off. So we have 2 modes of running the airplane. One is in vertical and the other one is in propulsion mode. So at the moment, only the 4 motors are running. The 5th one, the horizontal one, is stationary. So we have control over the 4 motors through this lever. We can lose some altitude by decreasing the levers. This will effectively lower the running speed of each one of the 4 motors, which should make the aircraft lose a little bit of altitude. When we're ready to fly, we have a button to switch into propulsion mode. This will effectively turn on the 5th motor, and this should push the airplane forward. At this stage, we're flying forward and it's keeping a constant height, and we have control over the airplane. We should we take a slight left turn. Same thing for the right side. We can now switch back into vertical mode, and we're going to try and make a soft landing. Okay, this is the end of the demonstration. Thank you for watching it. I hope you learned something new. And for any questions, please reach us at opalrt.com. Thank you.